Hi, welcome to another edition of Linear Algebra. Today we are going to start with a new chapter on arithmetic of matrices. Let's go and see what is in store for us here. Okay, so at the very beginning of the semester, we said one of our goals is to redo calculus, but as our main ingredient, we are going to use matrices as opposed to just numbers. So from beginning of your mathematics training in elementary school all the way through calculus 1, you learn how to perform certain operations. Of course, you have addition, subtraction, multiplication, division, power, and the concept of a function. What we want to do is to do all of these with matrices. As we are going to see, the first two operations are not going to give us any challenge at all, just what you might think they are. Addition and subtraction or linear combination is going to be straightforward. And then as we go down this list, the problem becomes more and more sophisticated. And then we are going to add a couple of other operations as well. So suppose we have a matrix A and another matrix B. Our objective is to learn to make sense of adding the two of them, subtracting the two of them, perhaps combining all of these things with scalar multiplication as well. So by here we have learned a linear combination of matrices. Then we want to make sense of matrix multiplication, as in high school the multiplication sign is not written, and this is going to be taken as the multiplication of two matrices. There are many different styles of multiplication. We are going to take a quick look at that further down. Then we are going to come to the case of division. That notation is rarely used anywhere in linear algebra. The notation we are going to see would be something like A times B inverse, or perhaps A inverse times B, as the case might be. So that is going to be the way we are going to deal with the division later on. Power, well, we want to make sense of what is A cubed and A to power of 10 or something like that. So we are going to have quite a bit to say about raising a matrix to a power. Then functions. What does that mean? Well, you have learned about many functions in calculus. The question would be how to apply those concepts to matrices. For example, you have the exponential function. How do we make sense of exponential of a matrix? So that is the project for us for quite a while. Essentially, toward the end of the semester, we want to make sense of this one, and hopefully we can deliver on our promise of explaining how vibrations are going to be understood by linear algebra, and that's going to require this exponential. Okay, let's go do the easy ones first today. So easy one is just going to be addition and subtraction, and just some notation about matrices themselves. So first of all, a matrix is going to be a rectangular array of so what's a matrix? We have seen them, of course. A rectangular array of numbers. Well, this definition really doesn't do justice because this rectangular array reminds us of some sort of like a shoebox where you put the numbers in some locations and such. A matrix is a lot more than that. A matrix essentially uh, shows itself through these operations that we are going to talk about. But let's wait and see how that's going to work out. So if I have a rectangular array such as say 2, 3, 4, 7, 9, minus 1 and so on, we are going to refer to this thing as a 2 by 3 matrix. So this is going to be number of rows that is mentioned first, and then number of columns that is mentioned second. And these are going to be referred to as the elements. So this is elements or entries of matrix, each of them. Matrices come in a variety of sizes, and so that is something we want to get used to. We never had that in calculus and such. Everything was just a single number, and now all of a sudden we have to deal with the issue of the size of a matrix. So issue of size, sometimes a matrix shows up like this. The nickname for this thing would be a row vector, and or you might call it a row matrix. If you want to refer to the size of this thing, is a 1 by 3. So this is 1 by 3, is 1 row, 3 column. If I have something like 5, 9, 10, this is going to be referred to as a column matrix. Sorry, correct this. Or a column vector. This is of course going to be 3 by 1 matrix because we have 3 rows. So notice that I have 3 rows in this, and then I have just 1 column. So 1 column, and but I have 3 rows. Sometimes we want to refer to a general matrix, that is, we are leaving the issue of the number of rows and number of columns open, as the case might be. So a general matrix, a general matrix, let's call it W, might be written like this. So first entry, I might call it W11, W12, and so on I go. And the next row is W21, W22, and so on I go. And so on and so forth. Now let's go ahead and specify, well, how many rows and how many columns are we going to have. Suppose I have m rows. So the first index refers to the row number. So if I write here, the first number is a row number. The second number is a column number. So one thing to wrap our head around is this convention. You just have to memorize that. There is no way around that. So if I have m rows, then my last row will be labeled m1 and m2 and so on. And so suppose I have n columns. So column number, it shows up in the second place here. So there's going to be W1n, and this one will be W2n, and the last of this is going to be WMN. Okay, so that's a general matrix. We rarely deal with this type of general matrix, but it does show up in our definitions and so on. So now sometimes we want to abbreviate this. The two styles of abbreviation. One is to have these columns listed. So I might refer to this thing as like column 1 and then column 2 and all the way through column this is in column, so I'll have in columns here. Another style is that I might use abbreviation by rows. So this is going to be row 1, row 2, and this is going to be row M. So in that case I will refer to my idea by saying, okay, I had row 1, then I had row 2, and all the way to the last of these things was row number M. So these are abbreviation. So by columns, this is abbreviation by columns. This is the abbreviation by rows. So the idea is that these are each of them is one of the rows I had here. And let me put some dot here so that we are jumping from 2 to M. And in this case we are abbreviating by columns. This is column 1, column 2, and then the last column. Aside from these things, we have a case where this rectangular array actually turns out to be a square array. So in that case we refer to a square matrix. Square matrix, simply a matrix that is having same number of rows as columns. Suppose we have a 3 by 3 matrix. How would it be written? Like A11, A12, A13, A21, A22, A23, A31, A32, A33. So that is the new lifestyle we are going to have to handle these type of entries. Okay, in this situation we still have additional terminology to learn. This is the diagonal or the main diagonal of the matrix. There's another diagonal here, but more often than not we played with this one. So that's called the diagonal entries. So A11, A22, A33. You notice that the row and column numbers are the same. These are called the diagonal entries or diagonal elements. Sometimes everything other than these are zeros. Those type of matrices are extremely friendly matrices. They're essentially as close to numbers as we can get in linear algebra, and that is referred to as a diagonal matrix. Diagonal matrix means everything is a square matrix and everything off of the main diagonal is 0. So if I had 5, 6, 7, but these other entries were all zeros, so off diagonal, so these entries are called off diagonal. These are off diagonal entries are 0. So that is where my so diagonal entries, as we said, the friendliest matrices we can have. On lucky days we are dealing with diagonal matrices. Super lucky day would be when all the diagonal entries are all actually all the same, and of all of these things, one that stands out is so-called identity matrix. Identity matrix you have ones here. You remember when we had the issue of echelon and the row reduced echelon, that was the perfect thing we could expect. Close to this is the idea of a scalar matrix. Scalar matrix, the idea is that if I take this thing and double or triple, what would happen? Well, I will have just that number on the diagonal. So this is example of a scalar matrix. Scalar meaning this matrix for all practical purposes is going to be just like a number. We have a special notation for this thing is I, or sometimes we might indicate how big of an identity it is, meaning what's the size of this matrix. In this case, it's going to be 5 times I will be that particular scalar matrix. So in general, if we had the n by n case, so I sub n would mean n by n identity matrix, just like what we have. Of course, we are going to say two matrices are equal to each other if and only if they are of the same size and all the corresponding, so two requirements are here. Well, let me see. They must have same size for us to compare them, and then all corresponding entries are equal. To talk about the generic entry of this matrix, like something that is sitting inside of this array and we want to refer to it, tradition is to refer to this as the item that is seated at the location ij, meaning this is sitting in row I and it is sitting at column j. So if you want to pick out one representative of entries of a matrix, they typically refer to it as matrix with subscript element with subscript ij, and so in this case, if the two matrices are equal, it means the item at location ij of A same as the one for B, so that means all corresponding entries are the same. Okay, so now so far we just talked about the size. An issue of special matrices. Special matrices, one of the specialties of a matrix would be where are the zeros. So, and that brought us the issue of identity scalar, and we are going to have other ones. We had the issue of triangular matrices at the beginning of Gaussian elimination. That's going to come up here too. We are going to have upper triangular and lower triangular, and all sorts of ways of referring to where the zeros happen to be. So now let's go to the arithmetic. Arithmetic, oh well, where does our arithmetic start? Of course, arithmetic starts with addition and subtraction. So what is meant by A plus B? Well, exactly what you think it's supposed to mean. So suppose I have, let's write a simple matrix 2, 3, 4, 5, 6, 7, and I have another one. Now an issue comes up here. If you want to add and subtract, they must have same size. So we have the issue of compatibility condition. Compatibility meaning I cannot add 2 by 3 to a 5 by 7 or anything of that sort. They must match in their size completely. So if I have 1, minus 1, 3, 5, 2, 11, how do I add them? This is where that shoebox idea comes in. So there's nothing significant about the operation. You just add this component wise. So the operation meaning if the addition that you want to do, you're doing it between the items that are seated at the same location. So it's 2 plus 1, so that's your 3, and 3 plus minus 1, that's 2, and 4 plus 3, that's 7, and 5 and 5 is a 10, and 6 and 2 is an 8, and 7 and 11, what's 7 and 11? So it's 18. Okay, so if I have subtraction, it will be same issue. And if I had linear combination, let's do an example of a linear combination. So I leave the subtraction to you. 5, 6, 7, and say I have adding 3 times 1 minus 1, 3, 5, 2, 11. This is still component wise, meaning I'm taking 2 and doubling it, so that's a 4 and a 3, so I make a 7, and then a 6 and minus 3, I make a 3, and then you go ahead and fill up the rest of this thing. So so addition, subtraction, and addition, subtraction, linear combination. These are component-wise operations, is exactly like what you did in elementary school, and then that's about it. The only thing to watch out for is the compatibility. If they are not same size, you say the answer just does not exist or undefined and such, and you carry out the operation by component wise. You do it component wise. Next, the issue of, so that's the end of easy easy life. So next up is agenda. We are already done with this one and this one. We are now looking at multiplication. Okay, multiplication is going to take us a while to get used to that. We said as we go down the list, these things are going to become more and more complicated, exactly like what you had in elementary school. Multiplication took a while, and then division showed up, and this was, well, to call it correctly, a lot more painful than that one, and that, well, it goes on like that. So next up, we are going to have matrix multiplication. Matrix multiplication, our first approach perhaps would be, well, do just what you were doing here. 2 times 1, 3 times minus 1, 4 times 3, just do it component wise. And yes, you could do that, and there are some applications for that as well. Yeah, but it's not all that useful to allocate any space for it. There's some graphic application, you're going to see this, and so in your software, especially MATLAB software, you're going to see something of this sort. But as far as linear algebra is concerned, that kind of matrix multiplication is of very little use in the theory of linear algebra. Matrix multiplication starts with something that we have looked at the beginning of semester. Matrix multiplication ties in with dot product. So let me remind you what we had at the beginning of the semester. Beginning of semester, if I had a matrix, let me give it perhaps some different name so it does not. Suppose I had a vector, and this vector was 3, 6, 2, and then I had another vector, let's call it t, and that was, so 1, 7, 3. Then we had v dot t, first entry times the first entry, and the second entry times the second entry, third entry times the third entry, and then you do these multiplications, and then you add them up, and you call it your dot product. Sometimes you have another name for it called inner product, and perhaps even some other names. Okay, that is essentially the most useful style of multiplication in linear algebra. And there are other types. We even have the outer products and cross products and so on. But the one that stands out against the entire background of all sort of multiplication there is this dot product. Okay, we are going to build everything around that, except that we are going to add one more uh, sophistication to this, is how we are going to write them. So if I want to multiply these two with matrix multiplication, I will arrange them in a special way. That is, I put them uh, a row times a column, and then nothing in between them, so I don't put this dot anymore. When you are putting the dot, the convention is that you understand the first with first, second with second, third with third, and so on. So that's a dot product. When you want to do matrix multiplication, your first vector has to be written as a row, second vector has to be written as the column, and the idea is the same as here. That is, the first with the first, second with the second, third with the third. Then they have to be multiplying just like here. 3 times 1. I'm putting in parentheses to emphasize and also to protect against sign mistakes and such. So my operation will be exactly what I did here. Is 3 and 42 and a 6, and I get 51. This 51 that comes out of this thing, if you wish, you can think about it as a 1 by 1 matrix. Out comes 1 by 1. Now what? So this is a row vector, this is a column vectors. I might have several rows, which makes a big matrix for me. So let me write it here. Say 3, 6, 2, and then 5, 1, 4. I could have several of these columns. So for example, I can have 1, 7, 3, and then 2, 1, 1, and say 0, 4, 2. So what do I understand by this? So this is almost like a big example. We have to do plenty of dot products. That is, this row has to multiply this column, then that column, then that column. So there are 3 dot products. And then repeat again with the second row, with the first column, second column, third column. So there's 3 more dot products. All told, there's going to be 6 dot products. Each of them as expensive as this one. So quite a bit of activity is going on here, and that's where we are just moving away from that concept of a matrix as some sort of a shoe organizer, that you put just these things in it and that's all there is you are going to do, and perhaps you add and subtract by putting more shoes next to each other. This is very different from that concept of just a rectangular array. That's where we are beginning to give life to a matrix. So what do? We take an entire row of the first, column of the second, and then all the columns one by one, and then all the rows one by one. So all the rows of the first, all the columns of the second are going to multiply, and we have to write it out. Now first we have a compatibility condition. If you want to multiply a row and a column by this dot product, they better have the same number of entries on it. So we do have a major compatibility condition. If this is not there, then the product is just not defined. So how do we say that? One of several ways. The number of entries, so you have one entry, second entry, third entry here, then one entry, second entry, the third entry here, it has to match. How do we say it? So, well, this is the number of columns of you have. Number of columns of first matrix has to be equal to number of what? Well, this is number of rows of second matrix. Okay, number of columns of first has to be equal to number of rows of the second. And then what? Well, how about the size of what comes out? For each row here, you're going to have a row here. And for each column of that, you're going to have the number of columns here. So the size of the output, size of output product it's a matrix that has number of rows of first by number of columns of second. So this is a 2 by 3 and this is 3 by 3. These two have to match and output is going to be 2 by 3. So output of this thing, this 2 matches this 2 and this 3 matches this second of these 3's here. That's how the dimensionality is going to go. So, and then there is all the work that has to be done. So we said we have to do 6 of these things. So 362 by 173, that's the 51 that I had here. So first row and first column, and then first row with the second column. So 362 dotted with 211. So we don't write that dot typically. So 362 211. So that's going to be, you typically do this thing in your head and you don't write it down, but if you want to write it, I'll just go ahead and write it. So 6 and 6 and 2, so 2 times 3, 6 times 1, 2 times 1, and then I'll have my 14. So that's going to be my next number here. And then again 362 multiplied by 042, first with first, second with second, third with third, and that's going to be 28, and that's going to be written here. So where do the numbers get to be written? If I'm in row 1 and column 1, this is going to be row 1 and column 1, and this is row 1 and column 2, and this is going to be row 1 and column 3. That's here where the numbers get to be written. And then I am in row 2, so I'm row 2, I'll be dealing with 514 multiply with column 1 of the matrix here, 173. What do I get? So 5 and 7 and 12, and that becomes 24. That's where it's going to be written, 24. And then 514 multiplied by 211, so that's going to be 10 and a 1 and a 4. That seems to be, if I'm not mistaken, a 15 here. And finally 514 multiplied by 042, and it's going to be a, well, first is 0 and then a 4 and an 8, and that one looks like to be a 12. So sometimes to remember where we put everything and what it means for us to be compatible and so on, we might write this thing as a matter of just learning the stuff, but no book actually writes it like this. 362 514. I put the second matrix up here, 1 2 0 7 1 4 3 1 2. Okay, why did I write this? Just to pay attention to the following. that what we have here is a square matrix. The size that we have here is 3 by 3. That's the compatibility condition. So this is compatibility issue, that if you write the first matrix here and second one way up here, then the empty space here will be a square. Then comes the issue of, well, what is the output? The output is going to be the other empty square here. So 3, 6, 2, 5, 1, 4. This has 2 rows, and so does this. This has 3 columns, so does this one. So my output, that's going to be 51. Whatever we had here, 51, 14, 28, 24, 15, 12. That's going to be the output of our multiplication is going to be written here. Okay, so that is what is meant by matrix multiplication. Again, significantly more sophisticated and complicated than the addition and subtraction. We almost have no use for term by term or component wise multiplication. We said there's a little bit of application of that in a MATLAB software you're going to be definitely using later on, but outside of that, that kind of multiplication is of very little use. What we have is something built on inner product, so there is a lot of multiplication to be done. It's an expensive process. You can imagine if the matrices were bigger, it's a huge number of multiplication and addition has to be done. So that's the beginning of the flavor of the course and the complications that we are going to have, and so on. Now there are some simple examples to justify the concept of a dot product. They're a bit overly simplistic, but just to explain why would anybody multiply numbers like this, let me give a supremely simple example, and that example would be from a shopping list. So if you have a shopping list, you suppose you have you're buying apples, and of course it has to be alphabetical. So bananas, and who is it that starts with a C? I don't know, maybe you're going to buy cherries or something. So you're going to have a quantity. So maybe you want to buy 2 pounds and 3 pounds, and well, this is expensive, so you better stay to just 1 pound. And then you have another one, which is the price. So price, write it like this, just to see. So suppose the apples are $1.50 a pound, and the bananas are say 50 cents a pound, and the cherries, well, that's expensive, so $4 a pound. So if I have if I want to know how much my shopping list is going to cost me, well, of course 2 times 150 plus 3 times of 50 cents, and then 1 pound at $4 per pound. So I'll have $3 for the first item, $1.50 for the second item, and $4 for the last item, and that's going to be what, $8.50. That is my my bill. Now you can imagine that you can have several rows, perhaps people buying from different people are buying, so you're buying for yourself, and then you have a list from somebody else, you're buying for your neighbors as well. And then suppose this is one grocery store prices, and then there is another grocery store prices. So you can compare, the columns might represent different stores, and the rows might represent different customers. And then you'll have a quantity matrix times a price matrix, in outcomes lots of numbers, which would be the bottom line of each customer depending on which store they went to. So you can build a example of a problem like this, but of course we have much more sophisticated examples coming up later on that's going to help us to uh, yeah, further our goal. So our goal is to make sense of multiplication, then division, then power, then function. That's where we are going, and not all that interested in grocery shopping. So uh, let's go ahead and make a notation for the systems of equations that we had. So at the beginning of a semester, we justified why somebody might end up with this type of equations. So let's write a few equations here. Let me write, say, 5x 6y 7z is equal to, say, 12. Okay, so this was something we came across with a variety of meanings, intersection of two planes, or whatever you might have. You end up with system of equation like this. Then we come and say, well, another way of writing this thing is to isolate your coefficient matrix. So 2 3 4 5 6, I just wrote them like that so we remember who's where, and the unknown matrix x y z, and the right hand side is 11 12. So at the beginning of semester we had isolated this matrix and the right hand side, and we were applying the Gaussian elimination and so on. Now we are writing entire matrix notation with a matrix multiplication notation. So if you take the first row and multiply by the column here, this column is now our variables, unknown quantities x, y, z. What are you going to get? You get 2x plus 3y plus 4z, and that's exactly what this thing is. Well, 11 is on the right hand side. And then you take the second equation. How is the second equation encoded here? You have 5x and 6y plus 7z is equal to 12, and what your second equation is. So our matrix equations are going to look like some matrix, some vector of unknowns. So I might write a capital X indicating this is a vector or whatever it is, and then I have my right hand side, so whatever this matrix or vector is, let's call it B. So with all of this, all of a sudden we are going to see that the notation of matrix multiplication that we have makes our linear systems look like the items we had seen back in middle school. So over there you might have seen a simple equation like 2x is equal to 12, and you solve it and you say x is equal to 6 by dividing both sides by 2. Now we have a matrix times a vector of unknown quantities equal to the right hand side as it is here, and then of course is what we want to do is what we did here. Over there you say divide by 2, and that's what's going to bring us to our next topic. How do you divide by matrix? What are the complications that we are going to come across when we get there? So we are going to mention that in a future lecture. So first we want to do a little bit more practice on multiplication and special cases of multiplication and so on. So let me put that for future lectures so that this doesn't become super long, and then we come back and continue with this concept. Okay, so we need to become comfortable with this thing. So you remember back in elementary school you probably spent the whole year to learn about multiplication. First you had the multiplication table, and then multiplication of big numbers, and then maybe a couple of years you spent on that. So it would be wise if you spend a couple of weeks on multiplication, do as many exercises as you can. So we have few of them on the homework, but just pick the textbook and go through all the exercises there. The more of this you do, the more comfortable you're going to be with what's going to come up next. Okay, so I cannot emphasize this again. Just think you're back in elementary school and you're going to go through these things, and that's necessary for learning linear algebra. Okay, until next lecture, good luck and God bless.